can zoom in and out with the video.
You don't want to zoom in and out, but that was just focusing. You don't want to, it's just a digital zoom, so it doesn't really improve the quality. All right, so now we're back to finding the derivative function. It tells us the slope of any tangent line. But this is a fair amount of work, but it's less work than the other method we did yesterday. But now I want to go on to a shortcut for any monomial. There is something called the powers rule. The powers rule for any monomial, and it works for other things as well. Works for polynomials. Okay, I was going to try and prove it, but I think I just lost the time to do it. If you're looking at f of x equals a number times x raised to an exponent, there's a pattern you're going to find out happens. Take a look at this x squared and this 2x. It's not a mistake that after we went through that limit process, we wound up with that number. When you're taking a derivative of a polynomial, any coefficient you have just comes along for the ride. Okay? The exponent moves down, kind of like a logarithm, but that's the only similarity. It's coincidence that it behaves that way. It's not related to it. The exponent comes down as a coefficient, the variable comes along, and your new exponent is one less than whatever exponent you started with. And this will very quickly get you the derivative function of any polynomial, which is going to tell you the slope of a tangent line, which it turns out to be is how you find an instantaneous rate instead of an average rate. We did a lot of stuff with average rates in physics. Now we can start talking about impacts. Let's use a physics example since all of you were in physics. Quick note on this. Let me do a couple more examples first, then we'll do a physics example. Okay, quick example. Y equals 5x to the fourth. Y prime is a function that will tell me all about the slopes of tangent lines to 5x to the fourth. How would this pattern apply to that situation?
No, if you would.
You get 5, and then in parentheses 4x at the third.
Very good. Or just 20x cubed. That works. Congratulations. You found your first derivative with a powers rule. This is a magical moment.
It's not that bad.
This part isn't. It gets exciting. That limit process, you always have to go back to it at some point. True story, I was teaching this 2 springs ago. A former student of mine from another school graduated, went to college, became an engineer. He was a kid who always gave me a lot of crap about how doing it the long way with the limit was annoying because there always turns out to be a shortcut. There's one shortcut for polynomials though. Problem is when we get to sine, cosine, there's another shortcut. This doesn't work. Get to logarithms, exponential growth and decay, there's another shortcut. This doesn't work. And he told me that when he started doing heat transfer modeling as an engineer, just what happens if your warm hand picks up a cold glass and the glass starts to cool and your hand starts to cool and the glass starts to warm? You have to use derivatives and you have to go back to the limit version. You can't actually use these shortcuts. So you can never get completely away from it. But for polynomials, this is a nice shortcut. Another thing you can do, it turns out, the monomial rule can be expanded, distributed. So if I say what's the derivative of 3x squared plus 5x plus 2? First one's easy. Second one is a little more complicated. We'll go through those as we go through. What is y prime, the derivative, the formula for telling us the slopes of tangent lines? What is y prime going to be for my first term?
It would be 3.
6 times x.
Wait, you what?
I take the exponent and I bring it down to the front and then I subtract 1 so I get 6x to the first or just 6x. You bring down the n, any coefficient just comes along for the ride.
So why wouldn't you down bring 5? You didn't, 3. You didn't bring down 3.
I don't have a 3 in the exponent spot.
But doesn't the a have to come down first? Like in the...
3 is x.
Nope.
Yeah, exactly.
3 is my coefficient. Oh, I see what you're saying. Okay, let me write out the step the way I did over here. I'll show the step. The 3, when I say bring down the 3, I don't mean like bring it down from the exponent spot, I just mean bring it into your next line of work.
Yeah.
Okay? And then inside the parentheses, I bring the 2 down from its exponent spot, and I'm left with x to the first power.
Okay.
Alright?
Oh, you just skipped a step. Oh,
Yeah,
okay.
Jarabi said 6x, so I
Right.
figured he was ready to skip a step on this shortcut. For this one,
5.
it would be 5.
Yeah, you're
Well, what was my understood exponent here, Robbie?
1
1.
So this becomes 1 times x,
to the 0.
and anything to the 0 is
1.
awesome.
So it's 5.
It's 5, very good. What's
about-
going to happen to that plus 2?
Isn't
Yeah,
it
that's what I'm
going to be
saying.
nothing?
Do you have to bring it down?
Well, there is a way to look at this. There's a couple
Or
ways
it's
to
going to
look
be
at this.
plus 2?
Here's my favorite. It is, could I write that as 2 times x to the 0 power?
Yeah.
Because there would be 2 times 1. Right?
And then what would I, so if I could bring down the 2, and then in parentheses, I would have no room,
0.
but I would have 0 times x to the negative 1,
Yeah, so you get 0.
so I'll just 0. So the powers rule works there, it goes away. So my final derivative of this quadratic is
6x.
6x plus 5. So let's look at what happens. Terms with change with an x in them go down a degree. A term with just a coefficient in x, only the coefficient remains. And if the term is a constant, it goes away
Wait a minute.
completely.
Is that always like
Is
if you have...
anything
yeah.
times 0 with 1, right?
Anything raised to the 0 is 1.
Yeah, so you still. Oh, true. I guess. Yeah, right.
Okay. Anything times 0 is 0.
But how do you not have the?
Just
Which term? The 5x or the 2 or the 2?
I don't get how you got rid of the 2.
Okay. A couple ways to think of it. I have 2x to the 0, right?
Yeah.
The first thing I do is I bring down the exponent as a coefficient. What's
Yeah.
0 times anything?
0.
So it's all gone.
Oh,
That 0 makes that go away.
that's weird.
What if you have like a
Um,
3x to the 4th power? Would that drop down to...
3x to the 4th power would have become 12x to the cubed.
So no matter what exponent you have, it always drops one level?
Yes.
Okay.
That will, and this rule turns out to work for fractional exponents. That will get confusing. People will make silly mistakes on that. But I want to talk conceptually about another way to remember this as well. 3x squared went to 6x. 5x went to 5. Let's look at each one separately. The quadratic went to the line. That's dropping one level, as you put it. Derivatives are talking about how something is changing. Okay, it's about how something is changing. 5x, if you just graphed y equals 5x, you'd get a line, right?
Yeah.
That's a constant change. It's changing by the same amount every time. If you take the derivative of a line, you just get the slope of that line. So the derivative of a line at an angle is just a horizontal line. We started out with just plus 2, correct?
Correct.
Here for this term. Plus 2 is not changing. It's a constant term. There's no change here. A derivative describes how much something is changing. If you just have plus 2, is that 2 changing? There's no x, there's no variable, there's nothing varying, there's no change. That's the other reason it goes away. If what you're looking at doesn't describe a change, the derivative has nothing to say about it, nothing to tell you about it.
But in the derivative, 5 is not doing anything. It's not changing anything, right?
Well, now in the derivative, the 5 is not changing, but remember in the original function, it was 5 times x. There was change. What was the change? It was 5, it was a rise of 5 for a run of 1. The derivative says that was the change.
Okay.
Derivative describes how the original function was changing. So that's the shortcut for the powers rule. I want to show you a very specific example of it. And I was not proving where this came from, but instead you may jump ahead to doing it backwards.
what?
Anti-deriving.
So changing from 2 to 1?
Okay. But first I want to use a physics example. You guys remember x equals x initial
So AT squared.
plus v initial t plus 1/2 at
Yeah.
squared.
Yeah.
Okay, now this is your equation for position in physics as long as the acceleration is constant. As long as you're under a non-changing acceleration like gravity. Remember this one? All right, let's derive it. Actually, AP Calculus has questions about this, and for some reason that I actually don't know, they always call position S of t. I don't know why. Not worried about it. Well, let's see how well you get these ideas. S prime of t. Okay, you have started. This is describing your position as you accelerate constantly. Your initial position, is that a constant or a variable?
Initial is a constant.
Initial, it's a constant. You can't go back in time and change where you started the race, right?
No.
Okay, so this goes away when you take the derivative. Your initial velocity, is that a constant or a variable?
It's constant.
It's a constant. You can't go back in time and change where you started. What about your time? Is that?
It's changing.
That's changing, right? Okay, so this is just like 5 times x. So the variable is going to go away, and all that's going to remain is the v initial. This is like if I said y equals 5 times x, the 5 remains, the x goes away when you take the derivative. 1/2 coefficient. A is also a coefficient. What happens to t squared? That's the only variable part. That's the part that's
It
changing.
becomes 2t.
Becomes 2 times t. All right, let's simplify this a little bit.
It's the first power.
So s prime, yep, to the first power. So s prime of t is nothing, is v initial plus 1/2 times 2 cancels out, at. Does that formula look familiar?
Yeah.
What was that the formula for?
Is the not the speed for how we get.
That's your formula for velocity under constant acceleration. Velocity is the derivative of position. Take the derivative of a position function, you're getting a velocity function. What happens if we take the derivative again? We take a double derivative, indicated by 2 apostrophes.
You can do that.
Yeah. And that's going to be the same as taking the first derivative of the velocity. V initial, constant,
Yes.
goes away. Constant times a variable. Only the constant remains. The second derivative of your position is the first derivative of your velocity, is your acceleration. These two formulas have been derivatives of each other all years. Remember I used to turn to Tyler, who was in calculus, and say, you had better never forget the difference between these two? All he had to do was remember this one, and he could take the derivative of it, and he would have the velocity.
That's an unfair advantage.
It's an unfair advantage at this point in his life, but he earned it. We got into calculus a year ahead of the rest of the class. So. But that's one use of the derivative. Okay? I'm going to do a couple more examples of it. Erase this rule, see how well you remember it. Now you know it works for polynomials. Let's see. If y equals 3x to the 4th plus 4x squared plus 9. Y prime, the derivative function. What is that?
Yeah, 3 times.
It's going to be 12
4.
to the...
Yeah.
Let Diego say the steps. But okay, Danny, jump to the next one. What's that one going to be?
Alright. 8 to the x. 8 times x.
8 times x, because you're going to do that. And
Yeah.
what's going to happen with the 9?
It's gonna go away.
It's going to go away. It was never there. So the final answer will be 12x cubed plus 8x. A ton of this in AP Calculus, but when you get to the AP exam, the multiple choice, sometimes they just require you to know formulas like that. The free response are all about, okay, here's the derivative. What does it mean? Those are where it gets difficult.
Do you have to say it in English or in math?
Little of both. They often say justify your answer. And sometimes you can justify it in English. Sometimes you have to remember a specific theorem. Give them a name they want. Anti-deriving. Anti-deriving. We'll talk about why you want to anti-derive tomorrow. But anti-deriving is if you're looking at a derivative, can you figure out where it must have come from? There is a formula, but I want you guys to struggle a little bit. So I'm going to tell you that y prime is 3x squared plus 5. What do you think y was?
Well, you know you're gonna have a 5x,
Okay, the 5x, good. 5 is going to go to 5x. Excellent.
and then
That's
the
real
x
quick.
is gonna go to x to the third.
Wow.
Oh, no, yeah,
Yeah, you're right. X to the third
plus 5x.
plus 5x. Here's the most important thing, not the most important thing. Here's a very important thing that is the easiest thing kids mess up on the AP exam and other places in calculus. If there had been a number here, what would have happened to it when we took the derivative?
It would have gone away.
It would have gone away. Diego's getting good at this game. Does everyone else see that? If there had been plus 12, when we took the derivative, it would have gone away. If there had been plus 57, plus pi, plus e, plus anything, it
So
would
how
have
do
gone
you
away.
find that?
We don't. Not yet. Sometimes we do. That's later in the game. But right now we write plus c. And plus c means there might have been a number there. It might have been 0. We don't know what it was. But when you're just anti-deriving with no other information, sometimes they'll give you other information. They'll tell you how to find c. C in a physics problem, maybe this was your initial velocity or your initial position. So maybe they'll give you information like that. But if you are just given, here's a derivative, what was the original function? You have to put a plus c there to say, I have no clue what number might have been there.
Are we gonna learn how to do that? How to find what number was there?
Tomorrow you'll learn more, I'll tell you more about that. Sometimes yes, sometimes
I
no.
mean, how could you though? I mean, unless they give you.
You need other information.
Yeah.
It needs to be a physics problem. They need to sit, it needs to be a physics problem where they give you the velocity and tell you your initial position. Then plus c is your initial position. They need to say this function passes through a certain point, and then you plug in the x, plug in the y of that point, and solve for c. They need to give you some other information. But in general, there will be a lot of problems where you'll just put a plus c at the end. They'll just say anti-derive in general. I'll show you that notation.
That's irritating.
Well, it's
I mean,
just
it's
saying.
kind of like I'm glad we know it works when you're out, but it's kind of just like
Wait,
it's unsatisfying. You know?
I understand exactly what you're saying.
When
There's something
you-
called an indefinite integral. I'll tell you what that is tomorrow, and that always ends in a plus c. It
I have
just
a
does.
question.
Yes.
I mean, this might be kind of stupid. Wouldn't you be missing a term here? Because you go from x to the cubed to plus 5. Wouldn't you need x squared somewhere?
No, it's not like you're thinking like polynomial long division where you always have to
Yeah.
fill in. You would not be wrong to put a plus 0 x squared in here, but
You don't
there
need
is when you're going through the multiple choice AP questions, there will never be a plus 0 x squared.
No, it's just that
Yeah, you're not under obligation to have a term of every degree.
Okay.
And I'm just skipping around to see if you guys are paying attention with that. All right, you're ready for one more rule actually, because Diego saw the 3x squared x cubed pattern quickly. But what if you don't have a handy? What if this coefficient is not the obvious? Doesn't go away so obviously. I mean, you saw that if you added 1 to this, you get 3, so that's where the 3 must have come from. But if I give an example like just y prime is, I don't know, just x to the 4th plus 4x squared. I'm skipping around terms. Now, let's think this through a minute. This x to the 4th must come from 5, because we were subtracting something, right?
Oh.
Okay, so this must have been x to the 5th to start with. Now, if I started with x to the 5th and I derived, I would have gotten 5x to the 4th, but I don't have a 5 here. Danny, you got an
Is
idea?
there a 0?
0 would get rid of the whole term. That
Oh,
would
that's
be
the
bad.
point.
But you got the right idea. What would get rid of?
1/5?
Another.
1/5.
Danny may have gotten that faster than almost any other year. Robbie, Danny's right, but were you going to say the same thing? Or? Okay, so basically, we know that if we have x to the 4th in our derivative, we must have started with x to the 5th. And we know that the rule for taking the derivative would be multiply, bring down the 5. But there wasn't a 5 here.
You know,
So there
1/5?
must have been a 1/5 here to make it go away. So there must have been a 1/5 here, so that when we take the derivative, we bring down the 5, it multiplies by the 1/5, that's why we just have x to the 4th there. You can work out the same thing with just the x cubed here. the original function must have had a 4 in it. The original, this squared, remember this is the original function, this is the derivative. This squared must have come from a cubed, so what must have been in front of this one, since that 3 wasn't there? 1/3, the reciprocal. To get rid of the 3 that taking the derivative would have caused to appear, there must have been a 1/3 there. And then, we're going to get red because I can't stress it enough, there may have been a number there. So we have to indicate that. So this is y equals 1/5 x to the 5th plus 4/3 x cubed plus c is the general function that has a derivative of x to the 4th plus 4x squared.
Can they ever write in the derivative plus x, plus c, to indicate that there might have been some number there, but they don't know what it was? They don't know.
There's some crazy problems towards the end of AP Calculus where you're having to keep track of multiple c's. Like you're starting, they'll start you with like the second derivative, and you'll add a c sub 1, and then you'll antiderive again, and you'll add a c sub 2, and then they'll give you some other information to solve for those.
Crazy.
Yeah, it gets a little bit nutty, but
How many derivatives can you take from one function, or one thing?
as many as you want. But if you start with a polynomial, well, let's see. You're skipping way ahead, but I like this. If you start with x cubed,
Right.
you're going to go to x squared. Second derivative will get you to x. Third derivative will get you to a number. Fourth derivative would get you to 0. Every derivative after that will be to 0.
So you can only really, if you can only find out as many as you have the
One more than the degree of the
exponent.
That's as many as you can go with a polynomial.
All right.
Turns out when you get to transcendental functions, sines, cosines, exponential growth and decay, logarithms, things like that, you're going to get, you can sometimes get repeating patterns. You get derivatives that can go over and on forever with slight changes to the, that's actually fun stuff. We're actually not going to get to that this year. That's pretty much the beginning of next year. But yeah, sines, the derivative of sine turns out to be cosine. The derivative of cosine turns out to be negative sine. So then you take the derivative of the negative sine, you get negative cosine. Take the derivative of that, you're back to positive sine, and then the cycle just goes on forever.
Okay.
So you can, just like sines and cosines go up and down forever, you can take the derivatives of sines and cosines forever. In real-world application, the most common application of the derivative is, if your function is position, the derivative is velocity, the second derivative is acceleration. The third derivative is that idea I mentioned in physics called jerk, which is rapid changes in acceleration. And if you need to go beyond that to actually describe something moving, that's ridiculous precision. I mean, for the moon launch, they really only had to care about down to jerk. They care about position, velocity, acceleration, jerk. I don't think they took a fifth derivative or anything like that.
So how would you apply derivatives to the cold and warm water?
Wow, okay, now you're jumping way ahead. Why don't you take the course next year? Maybe we'll get to a little of that towards the end.
I mean, you're not really changing your position or anything. You're just changing like the temperature.
Now, it turns out a derivative can describe any rate.
Oh, okay.
Can derive absolutely any rate. It turns out anti-deriving can describe anything you accumulate, anything you gain or lose.
Oh.
So if you anti-derive velocity, you can think of it as gaining or losing position. One of the last things we reviewed this year for the AP Calculus exam was a problem where they were talking about the average number of people in line to buy concert tickets and how the amount of people in the line was changing. And it's one of the ones, I think it was a 2011 or 2012 free response question in the AP exam. And it's very hard to picture how, like, it's fairly easy, if you take in physics, picturing position, velocity, and acceleration is relatively straightforward. But trying to say how do derivatives and antiderivatives describe the rate at which people are getting in and out of a line to buy tickets, things like that can be a little harder to visualize. But you do. You guys are ready for some homework? You guys are lucky. The homework I'm going to give you is only about the shortcuts, but we are going to review next week.
Nice.
It's that longer way we did the derivative at the beginning. There's going to be at least one problem on your final that says, here's a function, here is its derivative, use the limit method to prove it.
We're going to go over that more, I know, right?
We're going to go over that more.
Okay.
Do a couple more examples of that. And I may do the general proof yet. But you guys are ready for the homework, so I'm going to stop recording at this point.